Okay, guys, how's the first one look? Pretty straightforward, hopefully. Second one on the end, pretty straightforward, hopefully. One on the end is an isolated lone pair. All the other ones are conjugated. Isolated lone pair is going to be more reactive as a base. And a nucleophile, it's not delocalized. Yep.
How'd you get 8
Did we get 8 for number 3? Pi bond here, 2 electrons. Pi bond here, 2 electrons. One lone pair is in a p orbital. That makes 2, 4, 6. And then a pi bond here makes 8.
But it's a triple bond.
Triple bond.
Oh, but it's going to be perpendicular.
Yeah, but it's not conjugated.
I didn't get the same logic. I counted the triple bond as 2, but I didn't count
If we draw the structure of the molecule, pi bond here. Anybody know what a pi bond is? Electron and p orbital, 1 electron and p orbital overlapping to make pi bond. It's a 2 electron bond. There's then an alkene here. 1 electron, 1 electron. That's actually conjugated here, yeah? They're next to each other. Then you have nitrogen. What's the hybridization of the nitrogen? sp2. One of the lone pairs is in a p orbital, because anytime a lone pair is next to a p orbital, it wants to be in a p orbital. So that's conjugated. Then we have a carbon that has there to a nitrogen. See, this is conjugated. I mean, there's another p orbital here, but the other p orbital, the 2 orbitals are coming out. 2 and overlapping, side to side. Make up the second pi bond here. But this pi bond is not conjugating with all that. If that's all on the board, this is all sticking out. And then this lone pair is in a hybrid. Here you go. 1, 2, 3, 4, 5, 6, 7, 8. It's its basic structure. I mean, we did stuff like that week 1, week 2. You need to understand structure of the pi system, p orbitals. I don't know that I saw anybody. I think I saw one that had 8. How many people got it correct? You know we already got it correct, or was it just a good guess? After seeing me do it, does it look like 8?
Yeah.
Why does it not look like 8?
I'm sorry. I assumed you were going to ask me.
That way is. Who doesn't understand that up there? If you don't, you need to work to understand that. It's basic structure of organic molecules. P orbitals. Really, the only thing new here is, everybody know that the middle nitrogen is going to have 1 lone pair in a p orbital? I mean, that's it. Do you not understand when there's two p orbitals, they are perpendicular to each other? You learned that in Gen Chem, right? Orthogonal, perpendicular. To overlap, they all have to be lined up. I mean, these can be overlapping, but this one is not. It's 90 degrees. Basic structure, 8. How we do? Second one there? Pretty straightforward. How we do on that one? Questions about that one? You can look it over here. I looked at both possible cations. Both cations are resonance stabilized. Best one is this up here, where you have the H out here, you get this plus, and you come over and you get that. Not only is it tertiary, but it's also resonance stabilized by the phenyl. That really didn't matter because the other one is secondary primary. Tertiary secondary is better than secondary primary. Up there, we're doing heat, so we get the most stable. Most stable would be where the chlorine's there because the alkene is tetrasubstituted. Not only is it tetrasubstituted, it's conjugated with the ring. That's actually a 1,2 product. The 1,4 product from up here would be adding chlorine here. Which one is that?
Third one.
Yeah. Here's the new H. That's a 1,4 product, but it's not the most stable. The double bond is only trisubstituted. There it's tetrasubstituted. Diels-Alder, 4 plus 2 is 6. Put the bridge back on there. The groups over here are strands. And then the acylium ion. Here, this is the major resonance structure of the acylium ion. Question?
Number 5, is it okay to write plus the enantiomer? Or no?
Number 5?
Yeah.
Yeah, you would also get an enantiomer because it is a chiral product. Question?
You do the triple bond not linear, but you do it straight up. Is that right?
Well, I mean, I didn't do it right here. Right there, it's actually supposed to be linear because it's SP. Yeah. There's no change in geometry with resonance structures. They're both linear. If you didn't draw it linear, it's probably okay, but you need to know that it's actually linear. It's SP. SP is linear. Major resonance structure? No, I was looking for which one's main. Okay, hopefully you learned a little bit about what you need to be working on. Any questions about the quiz? Those in Dr. Meow's lab, your mass specs are ready to be picked up there in his mailbox. Your name or group name should be on each mass spec. He said you could get them out of his mailbox in the main office. We'll get this posted. Okay, substitution reactions. We left off, we were looking at ethyl chloride, ethyl chloride. You got a p orbital next door to the transition state. You can really stabilize the transition state. Because of that, all these up here are quite toxic. Why are they toxic? Because your body's full of nucleophiles. You have DNA, which has like amino groups. Amino groups can be nucleophilic. The nucleophile comes in and kicks off the leaving group. You get SN2 substitution. DNA, alkylating your DNA via SN2 substitution. You don't want to be exposed to these that are alkylating your DNA or proteins. You know. Again, something like this is not quite as reactive. What are we doing right now? We're looking at the reactivity of the electrophiles in the SN2 reaction. What is the electrophile? That's the thing in the leaving group. Okay, so make sure you know what we're looking at. We're looking at the various aspects of these guys. Later on, we'll look at the nucleophile. All ready to go? Effective carbon substitution. Number 2. As you increase the carbon substitution at the carbon, we're attacking a carbon and kicking off a leaving group. As the carbon that we're attacking, as you start getting more substitution on it by other carbons, we'll see that we slow down the rate. This is just methyl bromide. It's the fastest. Its rate is greater than this. That's called a primary halide because the bromine's on the primary carbon. Why is it called primary? Because it's bonded to one other carbon. Secondary halide. It's even slower. The rate is faster. As I go across, I'm getting slower. The rate is slower. Tertiary halide. If the leaving group is on a tertiary carbon, the rate is so slow that we consider it negligible and we say it doesn't happen with SN2. Don't do SN2 with a tertiary halide. Everybody repeat. Don't do SN2 with a tertiary halide. I'm not going to do SN2 with a tertiary halide. Okay? This is fastest. Why? This is just steric effects. Okay? It's easier to attack this carbon. There's nothing in the way. These H's are real small. You know, if we draw out the H's, you know, they're actually quite small. And the nucleophile, boom, it can just get in there. Come in there and attack and kick off the bromine. Over here, we join that one H, but there's also H's all around these guys. I mean, they're small. But this is just, it's just more crowded. It can't get in there. Of course, over here, okay, remember there's H's here. Okay, it's basically just a crowding effect called sterics. That's a more technical term. You know, just like your arms. If my arms are right here, like football, you can't get to me. But if I remove my arms, you got a clear shot at me, right? It's kind of like that. So that's your basic trends. Steric hindrance, sterics. Steric hindrance negatively affects the rate of an SN2 reaction. SN2 is very dependent on sterics. Never do SN2 with tertiary halide. On the other hand, the above trend is just the opposite if we do an SN1, because in an SN1, what intermediate do you form? Carbocation. Which carbocation is going to be best up there? Tertiary. Yeah, you'd rather form tertiary. The trend is just the opposite with SN1. We'll eventually get to SN1 and state the trends again. Here's just some example rates. If you take some type of carbo to bromine reacted with lithium iodide, that's lithium spectator ion, you're reacting with I minus. One halogen replacing another. These electrons attack the R, kick off the bromine. Good old SN2, acetone's a common solvent for this. Now we got the I bonded there. Here's your rates. Methyl bromide. Well, they give a rate. Ethyl bromide are 1. Methyl bromide is 163 times faster. From here, you start doing the secondary. You see how much slower it gets compared to that one? And then that one's negligible. So those are some exact rates of that particular reaction. Methyl bromide, very reactive in SN2, even though it doesn't have a p orbital next door. It's so reactive just because it's like open season on that carbon. There's nothing blocking it. Nucleophile, bam, coming in. Methyl bromide is quite toxic. Easily alkylates things. Nucleophiles, boom, attack. Methyl bromide is used as a fumigant. It's a gas. It's not used in houses because it's too dangerous. Methyl bromide is you have a big warehouse, like 10 stories tall in New York. It's 100 years old, full of rats and everything. They'll go and just spray methyl bromide everywhere, and the next day everything's dead. Because all the biological molecules of the rat just got alkylated. All the nucleophiles attack the methyl and kick off the bromine. Again, something like this is not going to be quite as toxic. And of course, if you want to do chemistry here, you're going to have to maybe heat these to get them to react. Here, don't do SN2 there. While we're on the topic of steric hindrance, I make a note right here. We'll see sterics a good bit. Sterics slow down reactions. If the molecules can't come together, they're not going to react. An application of this is, I know some of you maybe are pre-dental, your anesthetics, local anesthetics like lidocaine, etidocaine. Some anesthetics are short-acting. They only last for 30 minutes. Others last maybe 3 or 4 hours. The ones that last longer have more steric hindrance, and that slows down the metabolism of them. So they last longer. They're not degraded as fast. But the chemistry of the metabolism isn't as fast because of steric hindrance. If you want to see that, look at the structures of these two. Now, the actual chemistry that takes place is an organic 2 reaction, carbonyl chemistry. You can still see the crowding around the carbonyl. Etidocaine has more crowding, or sterics, and the hydrolysis is slower. So steric hindrance is very influential on SN2. That's the main thing we're going to say about the substrate. P orbital next door, and then the idea of steric hindrance. Let's look at the leaving group. Actually, this is also the substrate. Sorry. but it's not the carbon. We're going to now look at the thing that's leaving. The leaving group. Your halogens are your best leaving groups, mainly because when it gets kicked off, it becomes minus, and you see Cl minus a lot, Br minus a lot, I minus a lot. Of your halogens, your iodine is your best leaving group. Bromine's next, then chlorine. So iodine is better than bromine, bromine is better than chlorine, and chlorine is way better than fluorine. Sort of the cutoff is here. These three are pretty good leaving groups. Chlorine's your worst. Fluorine is almost just, fluorine is a lousy, bad leaving group. For example, in the two reactions I show here, it's a little bit counterintuitive. It's a little bit counterintuitive. We can look at it. First, let me just show you the example of the reactivity. If you react this alkyl iodide with this, okay guys, group 1, group 2, those are just spectator ions. Anytime you see this, get rid of that guy there. What's the charge of this oxygen?
Negative.
Negative, because the potassium is plus, okay? That's methoxide. Your O is your nucleophile. These electrons attack the carbon, kick that off. You got a dipole here, that carbon's partial plus. That reaction's pretty easy up there. And we make I minus, okay? See, that's ionic. It's I minus K plus. Ignore your spectator ions. They got to be there, but they don't do anything. You try to do it down here, you're not going to displace the F. Very difficult to impossible. We say that the F is a poor leaving group. Because the chemistry just doesn't take place. It won't leave. Which substrate has more partial plus on the carbon, top or bottom?
Bottom.
Bottom actually does, because fluorine's more electronegative. Fluorine's more electronegative. More partial plus here. So what does that tell you? Is the degree of partial plus the most important thing? Apparently not. Apparently not, no. Let's look over here. Which is more stable? I minus or F minus? Which one? I minus. Why is I minus more stable? It's bigger. It's bigger. It's bigger. See, the more stable product is the one that's more willing to leave. F minus is actually not that stable. It's because it's so small, the charge is so localized. Yes, it's supposed to electronegative, but the size makes it not able to handle that minus charge. That's why HI is a stronger acid than HF. There's another thing. Iodine, because it's big, you remember the transition state? Where this is bonding and the leaving group is breaking? Because it's so big, this breaking can occur easier, and it's sort of like, here we go, I'm breaking, but because I'm so big, I'm like breaking. Fluorine is like, it just has to break. If you look at some reading, iodine is more polarizable. The electrons can sort of stay there a little bit longer. I can't give you a clear explanation, but it's something about the size of the iodine that also makes the breaking of the bond a little bit easier. We'll look at it and read about the real theory of it. In the end, what's your better halogen for leaving group? Iodine. That's your best halogen. Now, iodine compounds sometimes a little bit unstable. Also, bond strength. That plays into it. The CI is a weaker bond than the CF. So you're breaking the weaker bond. CF is just a strong bond. It's hard to break that. Iodine compounds are a little bit unstable. A lot of times they're hard to store. They'll do radical reactions easily because of the weak bond. Because of that, people don't often use iodine as your leaving group. It's more expensive. Bromine tends to be the most commonly employed, like in research. It's a good leaving group, not as expensive, it's stable. In industry, they use more chlorine. So much the worst of the leaving groups, but the reason they use it in industry is because chlorine compounds are so cheap. They can still get it to react. In the research lab, I'd probably prefer to have a bromine compound. Good leaving group, you know, but it's not going to like decompose on you and be finicky or expensive like an iodine compound. Okay, what about other leaving groups? Other than halogen, a variety of other atoms could be leaving groups. Let's look at a couple. What about oxygen? Oxygen by itself in the neutral state is not a good leaving group. You take this alcohol, you react it with OMe minus. I'm going to come in here and kick off this hydroxide, replace it with an OMe, kick off hydroxide. That's not going to react. This is a poor LG, poor leaving group. In the neutral state, as a neutral oxygen. Sometimes I wish oxygen was OX, because a lot of times you write an O, it looks like, is that really it? We're going to just draw a circle. So I'll call it OX. Okay, poor leaving group as a neutral oxygen. Now, if I get more specific, it's a poor leaving group in a rate-determining step. Quick question. In SN2, does a leaving group leave in the rate-determining step? Yes, it does. Okay. In organic 2, we'll see leaving groups leave in slow steps. I'm sorry, not slow steps. That's rate determinant. In organic 2, we'll see leaving groups leave in fast steps. If it leaves in a fast step, this doesn't apply. Oxygen can leave in a fast step in the neutral. But in a rate determining step, it's not going to leave. By the way, in SN1, does the leaving group leave in the rate determining step? Yes. You need to look at your mechanisms and be able to answer questions like that. Okay, so how do you make oxygen a better leaving group? Can you make it a better leaving group? Yes, you can make it a better leaving group by making it positive. Make it positive. We can do this transformation up here by including an acid. We're back to not erasing again. We include an acid, and the first thing that happens is you have to make this positive. You make it positive by protonating it. These electrons react with the acid. What do you get? This is a strong acid, okay? H+ implies strong acid. Now it will leave. A positive oxygen will leave. Now we can come in with our nucleophile. These electrons come in here, kick off the oxygen. A neutral oxygen is not leaving. Instead, we have a positive oxygen leaving. What does this arrow movement give? It doesn't give this directly because the oxygen has an H on it. It gives oxygen bonded to the carbon. Now, this oxygen has what bonded to it? A methyl and an H and one lone pair. That's now a positive. Lone pair bonded to carbon. What did we kick off? H2O. Yes. Up here, we're trying to kick off hydroxide. Hydroxide will not leave. Starting neutral, if you kick it off as hydroxide. Here, we have to make it positive, and what actually leaves, not hydroxide, but water. And we say water will be a good leaving group. But you got to turn this into water by first protonating it, then you can come in and kick it off. There's your SN2. This first step is like an activation step. Overall, we just did an SN2 substitution. I hear a lot of students saying, well, that's 2 steps. You said an SN1 is 1 step. Well, the substitution part was 1 step. It's just had an activation step that came first. Okay? I mean, this is not an SN2. This is not a step. Okay, hope you see the difference. Replacing the leaving group by the nucleophile was just 1 step. In the end, how do you make OH a better leaving group? Protonate it with a strong acid, make essentially the leaving group be water. And that will work. Why do I have to use methanol here and not O minus? Why can I not use O minus here? Doesn't it say that? Why not that? Why didn't we use that? I tried to use it up here. Because O minus would react with the H plus. You can't have your cake and eat it too. You can't say I want to be, because if you add an acid, that means you want it to be acidic. Well, this is like hydroxide, that's basic. You can't do a reaction with both acid and base in there at the same time.
That H over there, does the water pick that up and become hydronium, or does it just simply take the H off?
Oh, we didn't finish it up, did we? No. Something's got to take that. Well, what gave up the H here? There's got to be a minus. I like to reform the minus. You could form hydronium. What acid do you want to use here? You can't go to the stock room and say, give me some H plus. You got to get a minus with it. H what?
Seal.
H2SO4. Common strong acid for doing this. That means you got that and HSO4 minus. I'm not going to show full structure. I'm just going to kind of just do something like this. That takes the H. These electrons stay behind. Now the oxygen got 2 lone pairs, and what do we reform? H2SO4 reform. The H plus is what? It's catalyst. It acts by activating the oxygen to make it a good leaving group. You do your reaction, and then it has to give it back. Something has to give it back, and you reform your catalyst. So theoretically, all you need is 1 molecule of H2SO4, and it could just do it. Okay, oxygen. Oxygen's a great leaving group under acidic conditions. Under neutral or basic conditions, oxygen's not going to leave. How do we know? Because many people have tried in the lab and it just don't work. Okay, the top here is what I just kind of showed you. This experimental design is flawed. You can't say I got to have an H plus catalyst and then I'm going to react it with this. These two are incompatible. Acids and bases are not compatible. I mean, if you fill up your tub with hot water and cold water, what's it going to create? Warm water. You can't say, hey, my tub's full of hot and cold, and whenever I want it hot, I'll just pretend it's hot. Whenever I want it cold, I'll pretend it's cold. No. Once they mix, it's warm. The hot's gone, the cold's gone. They neutralize each other. Okay, thus a common reaction for alcohols is you can convert them to alkyl halides. Alkyl halide by reacting them with H halide or HX. Now HX is typically a strong acid, so that'll supply H plus. It also at the same time supplies the nucleophile. So we can show this ionized, H plus I minus. And that plus show the mechanism for going from here to here.
Like you don't add the acid and the base at the same time.
You can add the acid and it can protonate, but there's no nucleophile. I mean, we can protonate it, but if there's no nucleophile, it's going to attack it. Now you say, now you want to add in the nucleophile?
Yeah.
Okay. The problem is, acid-base reactions are always much faster than any other type of reaction. And I'll say that other times. Thanks for the opportunity to say that. This, you say, hey, I want you to only attack the carbon. It won't listen to you. This is going to take the H. That's an acid. That looks like H3O+. The base will just take the H. Having this attack here requires it to attack it exact way, exactly backside. I mean, it may approach like this. Only one in a whatever will attack exactly right. To attack at H is just a 1s orbital. You can attack it any way you want. Boom, it's much, acid-base reactions are instantaneous. If an acid-base reaction can take place, it's going to take place before any of your other reactions. So it's just going to take it. Unless you teach that guy to avoid the H. But it's hard to tell chemicals what to do. They won't listen to you. Well, we're back to, I don't know, we were doing so good for a couple of months. Well, it's the same old thing. This here, that would give that there. By the way, we can also mention this. This is an equilibrium here. Very often I don't talk about the equilibrium. I mean, this can go backwards. I mean, at this point we got this plus I minus. And that's a super strong acid. You'd have to know the pKa of this. This may actually be favored. But don't forget that's an equilibrium. We may mention that at some point. But at this point, you get this, these electrons. Now see here, this can take the H and you go back. But see, this is actually also, it doesn't like to take H's. That's why HI is so acidic. It'll let the other thing keep the H. And this will work. See, that's the base though. The base will take the H. That's not a good base. If it was, HI wouldn't be a strong acid. This comes in here, kicks that off. What do you get? You get the two products. Find SN2. You make OH, you're going to leave a group by protonating it. Show the product of the reaction below. I'm not going to erase this. It's a beautiful, beautiful ice. How we do? What'd you get? Did everybody protonate the oxygen?
Yeah.
Uh-huh. And at this point, the Br minus attacked the carbon, kicked off the oxygen. And when it got kicked off, what left? That. What did we form? That alpha bromide. Don't tell me you attacked over here and kicked the oxygen off of that carbon, did you? Is that a tetrahedral carbon? No, we only do substitution on tetrahedral carbons. See, this is the case where the oxygen is bonded to two carbons. We can theoretically attack either one, and okay, it doesn't have to be an OH. That's only bonded to one carbon. That's the only carbon you can attack. Here you got two, but guess what? You don't do SN2 on a sp2 carbon. Look back at the very top heading of the first page. I'm sure it said tetrahedral. Right? Good. How we do? Did some of you get that one right? Why didn't you get it right? You got it right?
No, I did the same thing.
You attack sp2 carbon? Question?
Yeah, since SN2 is inserted anyway, can we actually like draw it as one step? I noticed you always draw like that.
I did draw it as one step. The BR attacks the carbon, the leaving group leaves.
I mean, no, can you show like the oxygen electrons attacking the hydrogen and simultaneously?
No, that's an individual pre-activation step. I just skipped that step because I'm assuming that you could show the mechanism for getting there. Okay. I did it up above. Okay, what's another way to make oxygen a good leaving group? By the way, protonating is the most common. 90% of the time, that's what you'll do. But you can also make an OH a good leaving group by converting it to a tosylate. Tosylate is the introductory species we're going to convert it to. You can also convert it to mesylate, triflate. On the first page, it's actually a mesylate they use. Mesylates are very common in real-world research. For some reason, your textbooks just like to use tosylates. They're the same idea. Here they're shown. The tosylate is short for toluene sulfonyl 8. It's we used toluene in lab this week, didn't we? Benzene with a methyl, that's toluene. That's a sulfonyl, so it's toluene sulfonyl. And if that was a minus, it'd be an 8, but it's still kind of called an H. That's a tosylate, or a tosyl group when it's not a minus. Abbreviated to OTOS, that's actually not correct. It's strictly OTS. I like to abbreviate mine as TOS, but it's actually supposed to be just TS. Mesylate is methyl sulfonyl. Triflate is a little bit less common than mesylate, but it's actually the best. It's a trifluoromethyl sulfonyl, shortened to triflate. Let's see how these are formed and how they act, etc. Here's an alcohol. I've got a chiral alcohol. These are formed by reacting like tosyl chloride. Tosyl chloride would be, everything's the same up there. Okay, I'm about to blow your mind. The benzene ring system is, we can often abbreviate that as just sort of, I think that's like phi. P5 cosine phi. Very often aromatic, you can just sort of shorthand it with a phi symbol. But you need to know what tosylate is. And I'm not going to draw out the ring with the methyl in it. I'm just shorthanding it there, okay? The tosyl chloride is your tosyl, but over here instead of oxygen, it's got chlorine. That's tosyl chloride. Pyridine is, if we've seen pyridine before, we probably saw it with the acid base a little bit. It's a benzene with a nitrogen. Nitrogen is slightly basic, sp2 lone pair. These will get you your tosylate. O-tos, that's that. You need to know what this is. The oxygen is bonded to what? I mean, structurally, what? It's bonded to a sulfur with 2 oxygens and then the toluene. Okay? There's the oxygen of that. That oxygen used to be this oxygen. It's got a different kind of R group here. I'm not going to do this mechanism, but essentially it's a substitution. The problem is we got a pi bond here. It's a substitution. The oxygen replaces the chlorine. You got to get rid of the H. The base takes the H. Now the oxygen has replaced the chlorine. Again, I'm not going to show you the mechanism of the pi bond. We'll actually look at this again in Organic 2 at the very beginning, and we'll do mechanism there. Tosyl chloride pyridine is a very common way to get the tosylate. Then you can come in with a nucleophile, and you can displace it. These tosylates and mesylates, you do not have to protonate them for them to be a good leaving group. It's a good leaving group just like that. So no H plus needed. For example, we could react this with NaOMe and we'd be good to go. There's nothing to destroy this. The OMe would just, boom, come in here and kick off the tosylate. Then you'd have an OMe there as your nucleophile. Of course, that's bold, so what's going to be your stereochemistry now? Dash, because if the leaving group is forward, how does the nucleophile come in? From the back. Well, see, that's why I showed inversion, right? And there's no H plus to destroy your nucleophile here. These don't need to be activated. What's the leaving group look like when it gets kicked off? Well, it's O-tos. That's minus. We draw that out. That's toluene, right? But this is minus. It used to be bonded, it got kicked off. See, this is so stable compared to like hydroxide. Hydroxide won't leave, but that will. Why will this leave? It's stable. Why is it stable? Resonance. It's a very resonance stabilized anion. Sure, kick me off. I'm fine with just existing as a minus. I don't mind. It's a very resonance stabilized anion is the leaving group. You didn't need to protonate it. By the way, analogous to that is these guys like this. This is called dimethyl sulfate. If under my hands was H's, what would that be called? Sulfuric acid. You replace the H's with alkyl groups, you get so-called esters of sulfuric acid. This is called dimethyl sulfate. The other one is diethyl sulfate. These are very reactive. Nucleophile attacking the carbon, kicking off the oxygen. This being kicked off is very analogous to like a tosylate getting kicked off, except it just doesn't have a timing over here. It's got another O method. So it's a variation of the tosylate. But the reason to show it is these are very cheap. You can buy a gallon of this stuff for cheap. Okay. But it's also very dangerous. because that methyl being just a methyl, there's no stearates. But oxygen bound to the sulfur is a great leaving group. And these things are also very toxic. So it's just sort of a variation of the idea of tosylate, mesylate. If we look back on the front page, here's where we saw the mesylate. Now we can maybe look a little bit closer at what they're doing. How do they make the mesylate from 30? Here's the reactions. What is that? That's mesyl chloride. And pyridine, dichloromethane, OH to the mesylate. It's just like tosylate, except they use the mesylate version. Now they turn it into their leaving group. Now they come in with this amine, and the nitrogen's a nucleophile. And these electrons come in here and kick off the leaving group. Now the nitrogen's bonded there. Now the nitrogen has to lose an H to go neutral. What takes the H? Well, why do you think they included a base in the reaction? Something to take that H. So then they are using the mesylate to make ultimately they made the OH a better leaving group. How about nitrogen? Halogens, oxygen. How about nitrogen? Can it be a leaving group?
Yeah.
How do you know? Nitrogen can be a leaving group. What? You've heard of it? Just like oxygen, though, you need to make nitrogen what to make it a good leaving group? Positive. There may be some other unique ways like tosylate. You can make a nitrogen positive, it can be a leaving group. It's nowhere near as common as making oxygen positive. But there are some unique reactions where positive nitrogen can be. One of them is called the Heisig-Myers. I thought they only sold furniture, but they also do chemistry. If you react the tertiary amine with HI, you can get the secondary amine and methyl iodide. I want you to do a mechanism of this on your own, and pretty darn straightforward. What you don't want to do is get pigeonholed with these ideas. For example, we say you make oxygen better leaving, you're making it positive, and you're saying, well, alcohols. And then I give you an ether, and then you don't know how to deal with it. But you got to remember, I never said it had to be an alcohol. We said make oxygen positive. Oxygen can be in many different types of functional groups. But unfortunately, your book will probably just talk about alcohol. But really, it's any oxygen. It doesn't have to be an alcohol. That's a pretty straightforward mechanism if you just do it. Can sulfur be a leaving group? Yes. The sulfur is actually more common than way more common than nitrogen. Nitrogen is very rare. Your body actually uses sulfur a good bit as leaving groups. And as nucleophiles. Your body uses sulfur a good bit. Norepinephrine. In the body, it's converted to epinephrine. By the way, what does nor usually mean with chemicals? The only difference in the names is one's got nor and one doesn't, right? What does the nor mean? What's the difference in the structure? This one has an extra methyl or it's missing a methyl? It's what? Missing a methyl. Yeah, usually when you say nor something, it's usually missing something compared to the thing without the nor. What is that, like Italian or something? I mean Latin? Is it? Anybody know nor? I don't know. We got any Nordic people in here? I don't know what nor means. Neither? Neither nor?
Oh.
Basically it means it's missing something compared to the thing that doesn't have the nor in its name. Missing the methyl in this case. Your body puts the methyl on using this here, SAM. That's methionine. Adenosine. S-adenosine or adenylyl, something like that, methionine. You can actually buy SAM at the health counter as a supplement. And it will talk about being a methylating agent. The body needs methylating agents. It's a methylating agent. That's sulfur positive. That sulfur is a good leaving group. This nitrogen attacks that carbon, kicks off the sulfur. How do you make oxygen sulfur a better leaving group? Make it positive. Most common way is to protonate it. That sulfur's not protonated. It's made positive by another way. By being bonded to 3 carbons. Never said it had to be protonated. Next time you're at the pharmacy or grocery store, look up S-adenylyl methionine. You can find a bottle of it. We'll talk about methylation reactions in the body. So there's a sulfur being leaving group. What's next? Let's start looking at the nucleophile. So just look at the substrate, sterics, leaving groups. Now let's look at the nucleophile. You got to have a good nucleophile to do an SN2. What type of nucleophile is best? You need a good nucleophile. Good nucleophile is just like what I told you a good base was. What was a good base 6 weeks ago? What's your best bases? Anions and also what?
sp3.
Exactly. Those are also your good nucleophiles. Anions, sp3 nitrogens, sp2 nitrogen, reasonable also. Those are also your good nucleophiles. Neutrals can be nucleophiles, but it's going to require like high temperature. But that's absolute consideration. Comparatively, which is better nucleophile, hydroxide or water? Both of these are basically sources of OH. Which one's stronger nucleophile? Anions are more nucleophilic. Remember, we got a partial plus here. Which one's going to be more attracted to the partial plus? Minus. This makes sense, right? Okay. Which one's a better nucleophile over here? Obviously this one, right? Okay? That should be pretty straightforward. Your anions are more nucleophilic than your neutrals. There we had both for oxygen and both for nitrogens. Let's change it up a little bit. Which is a better nucleophile, ammonia or water? Oh, they're both neutral. So we have to look at something else. What's number 2 say? Ammonia is more nucleophilic. Why? It's the same reason as why it's more basic. It's less electronegative and does what? Which one holds the electrons tighter? Oxygen holds the electrons tighter. Nitrogen, the electrons aren't held as tight. I talked about how oxygen's a better parent, holds the kids tight. Nitrogen lets those kids get out there and do backside attack and stuff. All right? That makes sense?
Yeah.
Nitrogen, ammonia is a better base. It's also a better nucleophile. The electrons are more out there ready to go. They're not held close to home. What did I say up there, number 2? I just sort of kind of clarified it. You can read it. So those are in the same row. What about the same group? Which is a stronger, a better nucleophile, H2S or H2O? They're both neutral, so we can't use the anion neutral. This. Which is a better parent, O or S? O, more electronegative. Holds on to the electron. Sulfur is not a good parent. Sulfur is a great nucleophile, actually, and your body also uses sulfur a good bit as nucleophile. Which is better nucleophile, I minus or F minus? Oh, they're both anions. Which one is a better nucleophile? You may say, well, F minus is not as stable, it's going to be more eager to react. This is always kind of conflicting arguments here. I is more stable, but it's also a better nucleophile. That may be still conflicting. You say, well, shouldn't F be more? Which one's a better parent? F's a better parent, holds them tighter, but then you say, but it's less stable because it's smaller, so I don't know what to do. The size of the nucleophile and the leaving group is important. Iodines are a good leaving group because it's big and it's able to bond. The bond sort of breaks more slowly. It's hard to explain. The bigger size also helps it be a good nucleophile because it can start bonding quicker as it approaches. In the end, you can just use the worst parent. The worst parent's a better nucleophile. The worst parent's a better nucleophile. Really, you can just use what I said in number 2. The least electronegative atom is your better nucleophile, and that'll get you the answer, I think, all the time. We're trying to rationalize some of them. Sometimes you have to say, well, sterics. We talked about sterics with the leaving group compound. What about sterics with the nucleophile? Well, sterics also influences that negatively. Because if you've got a bromine attached to you and I want to attack you, kick off the bromine, if I've got groups coming off, I can't get to you because the groups are in the way. So the nucleophile also has that sterics. Look at these amines. They're all neutral. They're all nitrogens. The difference is substitution. Your primary amine is greater. It's a better nucleophile than the secondary. Primary just has one R group sticking out, and so it can just come in and bond. If we start having 2, it's like, I don't know where to move. It can come in like this. If you put 3 on there, it's the lone pair is sort of buried, and it's got all these wings on it. It can't get to the carbon to attack it. It's really just a simple steric effect. Primary amine is most. There's a little bit of argument here. I don't want to muddy the water. I'm going to say that this is the most reactive, but I'm actually lying to you. This is probably the most reactive. Anybody tell me why that one is? Because what's the other argument here? Can someone tell me an argument why this one's more reactive than this?
Electron donation.
Electron donation from what? Yes. You see here you got 2 groups donating. It makes the lone pair very electron rich. This only has 1. Then you say, well, this one's got 3 donating. Well, the problem is, yeah, it's more electron rich, but it turns out that the sterics are too much to bear. Actually, that's the most reactive because it's not a lot of sterics, and it's also got the donation. But I don't want to muddy the water. Primary amines are very reactive. Of course, I'm never going to trick you and say, hey, that's the answer. I told you this and that. Do you understand the argument? Okay. Very often in chemistry, there's dual arguments. And you have to just, well, the only way you're going to get the answer is to look up and find some experimental evidence of what actually happens in lab. This is most reaction based on sterics. An argument of electron donation, increasing the electron density, can help you understand why that was kind of reaction. Let's see where we're at, finish up. In terms of substitution nearby is also critical. In the previous example, the substitution was on the nucleophilic nitrogen atom. Here, the substitution is not on the oxygen, but it's on the atom next door. So we're talking about this being a nucleophile. But next door, there's substitution. Substitution next door can also be a steric hindrance. Maybe not as bad, but it can. In fact, this is called tert butoxide. T-butyl tertiary butoxide. It's pretty non-nucleophilic. It's often used as a base to elimination. Now, in about 3 days, we'll talk about this. I'll refer back to this. Let's finish up here. Got resonance. One more effect of the nucleophile. Then we'll start summing it up. And then there should be some examples to start working. No, actually, let me tell you this. Actually, what we're going to do is we're going to look at some specific SN2 reactions that have names and that give specific functional groups. For example, you can make an ester by doing an SN2 with a carboxylic acid. Okay? So we're going to do some specific SN2s. Please look ahead at those. Then we'll move on to SN1, which won't be as much there. Then we'll move on to elimination, which is the other handout I sent you by email. Anything else, guys? Questions?
Are you sure you want to elimination?
I don't think so. Yeah.
I haven't said elimination now? No. Nobody?
1%.
Okay. Yeah, well, it's ready to be sent out. I just didn't hit the send button.